Now you can share.
Okay. Can you see my screen?
Yes, I can see your screen.
Presentation mode में डाल देता हूँ and let's see. Okay, and you can see the pointer.
Yeah, I can see the pointer.
Okay.
So you're ready, but wait a minute,
Yes.
because I want the other students to join as well. Okay.
Okay, ma'am.
Okay, Danial, you can start.
Okay, ma'am. Acha. If at any point my voice is not clear, please let me know.
Okay.
Also, agar along the way कोई verbal feedback हो, तो that would be nice, so that I know that my voice is reaching you.
Okay.
So I'm starting now. Okay.
सरफराज, sorry, सरफराज आपने भी गौर से सुनना है, okay?
Okay, ma'am.
Yeah, because you're going to ask questions, and because this content then becomes a part of the course content. Okay, ठीक है, समझ आ रही है ना?
Yes, ma'am.
ये कोर्स का हिस्सा है. ओके, चले शाबाश.
Okay, so the topic of my presentation is the Higgs boson, and we are starting now. Okay, so before we talk about the Higgs boson, we want to have a background of the general area of physics that we're talking about. So here we have the standard model of particle physics. What this is sort of like, जिस तरह chemistry में we have the periodic table, उस तरह for particle physics we have this categorization. This lists
Danial,
all-
I'm sorry to interrupt you. Actually, there are students that I was adding. So can you please just start from the beginning again?
जी जी अच्छा. So what I was saying is that we start off with introducing what is called the standard model of elementary physics, so that we can build up to the Higgs boson. Now, what the standard model is this chemistry may we have the periodic table that lists all the elements in a systematic manner. Is tarah for particle physics, we have something called the standard model. Okay, this lists all the known fundamental particles. Okay, and I want to quickly go through it so that we can understand the Higgs in context. Okay, so we have three basic kinds of fundamental particles. We have here, जो purple में है, these are the quarks. Down here, green में we have the leptons, and on the side, यहाँ पे these are red में what are called the bosons. Right now, इनके जो purposes
Let's keep it, Daniel. Let's keep it in English, okay?
Okay, Chane, I'll keep it in English. Acha ji. So what we have here in purple, we have the quarks, right? These quarks, and isme the most common ones are the up quark and the down quark. And down here in green, we have the leptons. And when we think of the leptons, think electron. That's the most commonly thought of leptons. So the purple and the green, these together make up all substance, all matter that we know of. The red particles here, the bosons, those are what are called the force carrier particles. So those are responsible for the four fundamental forces of physics. Well, three fundamental forces, because the standard model doesn't account for gravity, but that's a different issue, right? So one thing that I want to talk about here is, if we zoom in, we see that we talk about the mass, the charge, and the spin. Okay, and the spin is something I want to focus on here. As you can see, for the purple particles and for the green particles, the spin number is a half integer value. Half for the purples, and again for the greens we have half. So this is one of the defining qualities of the fermions, right? Now we compare this with the red particles here, right? Now we can see here the spin value is a full integer, one here, and for the other two also we have 1 and 1, right? So now we talk about the latest addition to this compilation, and that's the Higgs particle. As you can see, the spin for this is 0. So it's still an integer, for which reason we still classify it as a boson, but it's not 1, it's a different integer value, it's 0. So we give it a special category of its own. We say that this is, as you can see in yellow here, it says this is a scalar boson because this number is 0. This is compared to the red particles, जिनको हम कहते हैं gauge bosons or vector bosons. So this is one important difference between the Higgs and the other bosons that we know of. Okay. So Higgs we can also see from this particle, just let me just rush through this. The mass of the Higgs, it's quite heavy. It has it's chargeless and massless. Okay. Now moving on to the next slide. Okay. This is just a quick refresher of what I think most of us already know. Photons, they are responsible for transmitting the electromagnetic force. Gluons, they are responsible for transmitting the, strong nuclear force, and the W and Z bosons, they mediate the weak nuclear force. So this is just enforcing the idea that the bosons are force carrier particles. Next slide. Okay, so next we ask, what does the Higgs boson do, right? So the simple answer is that it gives mass to the fundamental particles, and it does so by a process called the Higgs mechanism, right? And further, the Higgs boson is an excitation of the Higgs field. This is similar to how a photon is an excitation of the electromagnetic field. So those are like analogous concepts. Now, the idea is particles that interact with the field, with the Higgs field, they have mass through the Higgs mechanism. Particles that interact weakly with the field, they have a small mass. For example, the electrons and the up and down quarks. By contrast, the particles that interact strongly with the Higgs field, they have a large mass. So those are the top quarks and the W and Z bosons. So the strength of the coupling with the field tells you how massive the particle is going to be. Achha. At this point, there's a confusion that sometimes pops up that I want to address. You could ask the question, does that mean that everything in the universe has mass because of the Higgs boson? The answer is a big no. Why? Well, the Higgs boson only gives mass to the fundamental particles. So consider a proton, right? Now the mass of the proton is made up of 3 quarks written here, right? But if you were to sum up the masses of the 3 quarks, the answer is much less than the actual experimental mass of the proton, right? This is because most of the mass of the proton, 99% of its mass, comes from the kinetic energies of the quarks. And this is a separate process. It's already understood by physics. This has nothing to do with the Higgs. So only about 1% of the mass of the proton is attributable to the Higgs boson. The Higgs focuses on the elementary particles, the ones that I showed on the previous slide. Okay. Okay, now we're going to go through the historical timeline of how the Higgs was predicted and discovered. Okay, so Peter Higgs theorized the existence of the Higgs field in 1964, right? And he said that the Higgs boson, which is the topic of my presentation, was an excitation of the Higgs field. So we can, by analogy, we think of the photon being an excitation of the EM field. Those are both related concepts. So he predicted that such a particle would have 0 spin, 0 charge, and be massive. So at the time, there was no such particle known. That it was only a prediction, a theory based on the standard model. Right? Then we started the search for the Higgs boson, and it took quite a long time. It started in 1964, and for 50 years the search was ongoing. Right. So the problem with looking for the Higgs was that it decays very quickly. Right. So you can't look for it directly. It doesn't exist for long enough. So the physicists must look for it indirectly, which is that they look for the products of its decay, because it decays quickly. So first, in order to look for the Higgs, you must create the Higgs if such a thing is possible, right? And the way you do that is you collide particles together in an accelerator. And now the Higgs is a massive particle, right? And the range of energies is between 115 GeV to 500 GeV. So because of that, when you collide particles together to try and create the Higgs, you must accelerate those particles to very high speeds. Only then do you have the mass energy needed to create such a massive particle. So this was done at CERN. Not all laboratories had the capability to deal with such high mass numbers, mass and energies. So this was done at CERN. Okay, so now one more issue is when Peter Higgs theorized the existence of the Higgs, the theory didn't predict the mass of the Higgs. So that was unknown. So the possible values they were gradually narrowed down to a range of values, right? So at one point it was believed that the range was in this range of figures between 150 and 600 GeV. Then over time, scientists further narrowed it down to 115 to 150 GeV. It was a gradual process. They were narrowing down the possible mass of the Higgs and what mass to look for in their experiments. Okay, so when we're looking for the Higgs, we look for the what it decays into. And the Higgs has several decay modes, as you can see here. A decay mode is, well, each possibility is a decay mode. So we say that the Higgs can first and foremost decay into a bottom quark and its antiparticle, or the Higgs can decay into a tau lepton and its antiparticle, or it can decay into two gamma photons, and so on, right? Now, we know that the most common decay mode is the first one, into the bottom quark and the antiparticle. And so we call this that this has a large branching ratio, that there's a high probability of this happening, right? But the problem with this is that it has what is called a large background, right? So if we were to look for the Higgs by looking for the bottom quark and its antiparticle, the issue is lots of other normal processes also produce these same pair of particles. So it would be hard to tell if we did find a bottom quark and its antiquark, is that because of the Higgs, or is it because of some other particles? So that's why we say it has a large background, and that makes it a bit of a difficult process to check for. The more likely best options to look for are the third option with the two gamma photons, or the last one with the two Z bosons. These are the ones that scientists then started to focus on when they were looking for the Higgs. Okay, so here is the theory. In the graph, you can see this green line here. Now, this green line tells you what you would normally expect to find in terms of the distribution of particles in a sample where there was no Higgs. So if you took a random sample in your experiments, you'd see that you have particles of different mass that you would find, and they would have different frequencies of occurrence, right? Now, if there was such a thing as the Higgs, that Higgs would decay into certain decay particles. Those decay particles would increase the number of the particles you would see at that given mass. That additional number of particles would show up as a bump on our graph. So this is what scientists were looking for. This is what they were aiming to find. If they would find a bump like this, and this bump was located at this point, which corresponded to the mass of the Higgs. Remember, we talked about narrowing down the range of values for mass. So in that narrow range, if we were to find this bump, that would be confirmation that we are indeed looking at the Higgs. But one of the problems was, this is an exaggerated graph. The actual prediction was that the bump would be quite small. So we had to make sure that that bump wasn't because of some statistical fluctuations. So because of that, we wanted a large amount of data, lots of repetitions of experiments to make sure that what we were looking at was actually something real and not a random bump. Okay? So because of that, the collision experiments were, as you can see here, run 40 million times per second. Right? So this created a lot of data, terabytes of data for the data analysts to go through and to make sense of. So it was a difficult, arduous task, lots of data to handle. So this is what scientists were looking for. And then in 2012, the CERN laboratory produced this result. Now, as you can see here, this is what the first thing I want you to look at is this. This is the bump that we were looking for, the blip on the graph. Now, the diagram at the bottom, it's the same thing, but with the background subtracted. So now everything is zeroed out except for what the signal that you get only due to the Higgs. So now you can see here that this bump is located very nicely in that predicted range of the Higgs. This is around 127 GeV. And remember that we had narrowed down our range to between 115 and 150 GeV. So well within our range. So this was big news. And because the experiment had been done so many times, it had what is called a 5 sigma certainty, which means that there was a less than 1 in a million chance that the result was due to a random statistical fluctuation. So very high probability that this was actually the Higgs. And another thing, what they captured here, this was due to this particular mode of decay, where the Higgs decayed into 2 gamma photons. This is what was found here, right? And for this success, the Nobel Prize for Physics was awarded to Peter Higgs in 2013 for his discovery of the Higgs mechanism and its experimental verification by discovery of the Higgs boson. So that 50-year-old theory was confirmed here. Now, okay, so we talk about some of the science behind the Higgs and in a very simplified manner. And I'll be using lots of comparisons and analogies to electromagnetism, because that makes for, it's a very suitable analogy, as you will see. Okay, the first thing I want to talk about, because it will come in later, useful later, is the energy of a field. Now here we already know that the electromagnetic field has an energy that is proportional to the square of its intensity. So that forms a parabola. As you can see here, the x-axis is the field intensity, right? Okay, how strong the electromagnetic field is. The y-axis tells you the energy of that field. So you can see here that as the field intensity increases, the energy of the field also goes up. Now, a key feature of this graph is that it touches the origin here. When the field value is 0, the energy is 0. We say that the vacuum expectation value of the field is 0. So somewhere far out in space, away from mass and away from any charges, the field energy would be 0, right? And this is how most fields are. But as you look to your right, this is the shape for the Higgs field. Now this shape, it's sometimes called a wine glass shape with the raised center, and some people also call it the Mexican hat shape. Now the key feature of this shape is, one more thing, the diagram is a three-dimensional diagram. You see the X, Y, and Z axes here. This is because the Higgs field is a complex field. So this axis is the real axis, and this Y axis, this is the imaginary axis, but you can forget about the imaginary axis for now. It's basically the same idea. The key feature of this field is that when the field intensity is 0, the energy of the field is non-zero. Conversely, when the field value is not 0, the energy of the field is 0. So this shape is going to come in it's going to prove very important, as we will see in the following slides. Okay, another thing that we need to understand before we can talk further is something called gauge theory. Now, what is gauge theory? Gauge theory is a theory that tells you that a physical quantity is going to be invariant under a gauge transformation. Again, a physical quantity is going to be invariant under a gauge transformation according to gauge theory. Now, we can make this easier, have this make sense by looking at a simple example. Consider the potential field, electric potential, and the fact that it gives rise to an electric field, which is the vector field. This is basic electrodynamics. Okay, we know that these two figures are related by this relation, that the electric field is equal to the negative gradient of the potential. Now, if all points in space had an additional value, constant value of C added to their potential, we would see that the E value remains the same. This is because the electric field strength is related to the potential difference, not the absolute value of the potential, right? Again, this is something that we study in electrodynamics, so nothing groundbreaking at this point. Okay, now, when I talk about adding C to V, right, replacing C with V plus C, this is the part that is the gauge transformation. This is what I talk about up here. And the fact that E remains unchanged, that means that there is a gauge invariance or gauge symmetry. This is the thing that I talked about up here, right? Okay, so now we have a basic understanding of the terms. One more thing. Okay. All right. So now that we know the basics of gauge theory, we can apply gauge theory to electrodynamics, right? And specifically we apply it to the electron wave function, right? And when we do that, gauge theory predicts two things. First of all, it predicts that a field of infinite range. We know that to be true because it's talking about the electromagnetic field. And the second thing that it predicts is that the quantum of that field would be massless. We know that's true because the photon is massless, right? So, and the fact that the photon is massless, this is of key importance because this means that the photon can travel at the speed of light. And that means that the associated field, EM field, has a very long range because its particle can travel very far, right? And this masslessness is due to the gauge theory here. This is what makes for the symmetry. It's the symmetry argument that tells you that the photon must be massless, right? And we see that gauge theory evidently is very successful and applied to electrodynamics. As you can see that both of his predictions are actually true. Now, when we try to apply gauge theory to the weak force, it predicts that the carriers of the weak force, which are the W and Z bosons, those must be massless, just like the photon is massless. But we know experimentally that W and Z bosons do have mass. They're quite massive. So this leads to the question, how can we preserve gauge symmetry and still have mass? So this is our conundrum. So we can reframe the question. We ask, how can you have a symmetric system, meaning that you have gauge invariance, produce an asymmetric outcome, meaning the W boson having mass? How can you have a symmetric system produce an asymmetric outcome? That's the question. And well, it seems very strange and paradoxical, but you see it all the time in other branches of physics. It's not such a new idea at all. Now, let me give you an example. Consider ferromagnetism. Now, we know that a magnetic material has tiny magnets, atomic sized tiny magnets that are aligned together. When they're aligned, the overall material is magnetic.
Just a moment, please. Sorry for the interruption. The announcement is that the meeting will end in a few minutes, okay, which is the Zoom restriction we have. So you can all click the same link again and rejoin the meeting, okay?
Okay, ma'am.
ठीक है?
Okay.
Okay, please continue.
Okay, so ferromagnetism. We know that if you heat a magnet beyond a certain temperature called the Curie temperature, the tiny magnets lose their alignment. Yeah, here's a little diagram for you. Okay. Now, if you were a tiny being living in this magnet, if you were right here where my dot is, and you looked around you, you would see whatever direction that you looked in, the tiny magnets are going to be randomly oriented, right? So everywhere that you looked, you would see the same thing, randomness. So we can see that rotational symmetry is preserved in this case. This lines up nicely with the theory because Maxwell's equations, all the physics theories that describe electromagnetism, those are also rotationally invariant. Maxwell's theory do not have a preferred direction in space. So everything is good so far. Now, when you cool it below the Curie temperature, then the little magnets become aligned, like here. Now, again, if you were a little person living inside this magnet and you looked around you, now you would see that rotational symmetry is broken because there is a preferred direction in space. If you would look around you, you would not see the same thing everywhere because all the little magnets point in one direction. So, as I said, rotational symmetry appears broken, right? But that is only because of the state of low energy. It's because the system is in its ground state, in its lowest energy state. And we know that Maxwell's laws are still intact, right? So the theory still tells you that electromagnetism is rotationally invariant, even though what you see at this low temperature is symmetry being broken, right? But this only appears that way because we know the theory tells us that electromagnetism is rotationally invariant. And further, the direction in which they align, this could have been in any direction. It's not necessary that they would always point up. So the alignment could have been in any direction. So we see from this that a symmetric system, meaning Maxwell's equations, has produced an asymmetric outcome, meaning that the tiny magnet's pointing one way, right? Now, we can apply this analogy to the Higgs field. All right, a quick background physics lesson. Okay, when the universe was first formed, it was very hot, right? And when it was hot, on this graph, we were at point A. This again is the wine glass shape that I talked about earlier for the Higgs field. When the universe was hot, we were up here at point A. At this point, the Higgs field had a zero intensity. The Higgs field was not active, which means that the elementary particles had no mass. Early on, the elementary particles did not have mass, surprisingly, and symmetry was preserved even in the most obvious sense. Now, as the universe cooled with age, we went to point B on the graph, and we saw that the energy went down because the universe cooled, and the Higgs field now has a non-zero value. The Higgs field has become active. It has started interacting with the fundamental particles, and now all the particles acquire mass. We say that this is spontaneous symmetry breaking because an asymmetric outcome has been produced. But gauge theory is still intact, similar to how in the previous example, Maxwell's equations were still intact. So a symmetric system, that is gauge invariance, has produced an asymmetric outcome, the W boson having mass. Okay, now we want to revisit a previous slide, but add a little bit of information to it with our newfound perspective. All right, please focus here on the electromagnetic field. Now, when we say that the photon is an excitation of this field, if you were to pay attention here for the animation, this means that there is an oscillation between these 2 points on this field. This is what a photon is, because when you have an oscillation here, what is happening is the value of the field, it goes from +2 to -2 to +2 to -2. This is how we know that the field is oscillating. And the energy value is up here constant. Now, a higher energy photon would look like this. This is a larger oscillation. It's still simple harmonic motion, but it has a larger size this time. Now, the same idea when applied to the Higgs field. What does a Higgs boson look like? Well, if you would focus your attention here, this is what the oscillation in the field is for a Higgs boson. You could also have the same oscillation on this side. It doesn't matter. This is like, part of the symmetry of the situation that you could, there's equal chance of the Higgs being here or here. Okay. So the chain of events that we see now is that if we try to give perspective to the discovery at CERN, the discovery of the Higgs boson led to the discovery of the excitation of the Higgs field, because that's what the Higgs field is. Now, the excitation of the Higgs field, once you know that there's an excitation of the Higgs field, you know that there is a field itself. And that led to the confirmation of spontaneous symmetry breaking, which we've discussed. That led to the confirmation of gauge invariance, that the fact that symmetry is actually preserved. And that led to the confirmation of the standard model, that one of the predictions of the standard model, that the Higgs particle should exist, proved to be true. So standard model again was verified. All of its experimental predictions were tested and found to be true. And this verification of the standard model is what resulted in the Nobel Prize for Peter Higgs. How many minutes are left?
It's okay, you can continue. Don't worry.
Okay.
Take your time.
I'm almost done. Okay, Acha, one more thing that I want to talk about is you could ask, how does the Higgs field give mass to particles, right? So again, by analogy to electromagnetism, we can we can have a basic understanding of how this happens. Now, imagine a water molecule. Right now, we know that a water molecule is a dipole. It has hydrogen at one end, oxygen at the other end. They have different electronegativities, partial positive on one side, partial negative on the other side, right? So place two water molecules here inside an electric field. The electric field is because these two plates, this is a positive plate, this is a negative plate. So the electric field is pointing downwards here, right? Place two water molecules in this field, but with opposite orientations. Here the negative side is up, and this here the positive side is upwards. Now, what happens is this water molecule is aligned with the external magnetic field. So this is in a state of low energy. Now you compare this with the other water molecule. Now this is not aligned with the external electric field. This means that this experiences what is called a dipole moment. It wants to turn so that it can be aligned with the field. And that means that this water molecule has potential energy. So if we were to figure out the mass of these two molecules, for the first one, we'd see that the mass is just the rest mass of the particle, the invariant mass. But for the other one, its total mass is equal to its invariant mass plus the mass due to the potential energy that it has. So this one would have slightly larger mass. So this is just an example, an analogy of how interaction with the field can affect mass, right? This example was presented by Leonard Susskind of Stanford. So just to explain a more complicated process. Okay, so what now the Higgs mechanism that was proposed, it was meant to explain why the W and Z bosons have mass, but it also ended up explaining why quarks and leptons have mass by a very, very similar explanation, right? So doing so, the entire